So far, we've been working with gravity a lot. Like, gravity's been a huge part of many of your calculations. Right? If I ask you to find the normal force is probably going to be equal to the gravitational force, which will be mass times gravity. Well, on Earth, gravity is 9.81 meters per second. Is gravity that same value everywhere in the universe? No, it actually isn't. Gravity is not consistent from place to place. On the surface of the Earth, it's quite consistent, but it's not everywhere else. And this is why I think this is one of the most important breakthroughs. Oh, I just lost these guys here. So that reloads. One of the most important breakthroughs, because without these sorts of calculations, I don't think we would have been able to send a man to land on the moon. Or we would be able to figure out how to send spaceships to go take pictures of other planets and discover how our universe worked. Does that make sense what I'm suggesting? So we can't just purely calculate gravity on Earth. We have to be able to calculate gravity anywhere in the universe, and that changes. Does that make sense? So, let me walk you through my lesson here. Are you guys still with me? I lost a connection there. Are you back up? Excellent. Okay, let's go. So review here real quick. Newton had 3 laws. I need you guys to know those 3 laws. So quick summary of those 3 laws. First law, usually it gets abbreviated to the term inertia. You guys remember that word? An object that is in motion will stay in motion unless something slows it down. An object that is not in motion will stay not in motion unless something causes it to move. Now, that piece of tape thing right there, it will stay there forever. But let's say an earthquake happened, and now there were some forces applying to it. Now it might actually move. Does that make sense? If any of you watched the movie Gravity, you see that movie?
Yeah.
If you were a space person who accidentally got untethered from your ship, this would be horrible and probably the most frightening thing in the world, and you started in motion in outer space away from your ship, you would continue in that straight motion forever. I mean, unless you had some sort of other force that you could use to maneuver you back the other way. Yeah.
I was thinking about what you said about throwing the ball and going the other way.
Yeah.
I don't think you would go the other way. You just spin the ball or anything.
That is true. That would be a major problem because it could cause a rotational factor. But if you could get it to be straight out of the center of your body, it is, in theory, it was possible. But you're right. That would actually cause spinning instead. Yeah. Which then again, you would then rotate like that for forever. Yeah. Terrifying, isn't it? Okay. So that's Newton's first law, inertia, basically. His second law is the formula that we've been using so often. Newton's second law is the sum or the net of all of your forces is equal to your mass times your acceleration. So that's Newton's second law. His third law is the one I want to focus on a bit more today. Newton's third law is the equal and opposite reaction law, where if something goes one direction, or if a force is applied in one direction, there should be a force somewhere else that was applied the opposite direction, kind of causing a push off. And I want to begin today by just revisiting that law. So I've got some more diagrams here. First 2 are about swimming. I found these online. I thought they were probably able to follow. Imagine that you're a person trying to push yourself in the water off of the wall here. You are applying a force where you are using your feet to kick off of the wall. But there is another force in play here, which would go the other way here. So there's wall on feet pushing you this way, and there's feet on wall pushing you this way. Does that make sense how there's 2 forces in play? But when we draw the free body diagram, I like this picture here. The system of interest is just the swimmer. So although yes, there is a force that would be trying to push the wall, trying to push the wall that way. Is the wall actually going to move though, probably? No. But it's not actually part of the system. So in the free body diagram, really we only draw the arrow this way as an applied force. But there was another force there. Same thing with swimming here. The reason why when you swim you go through the water is that the swimmer is pushing the water in the backwards direction, and so therefore the water exerts a force on the swimmer. So there are multiple forces here. Or this one here, if you push on the ground as a skateboarder, the ground is actually pushing back on you. Does that make sense so far? Okay, well, Newton came to a conclusion. I wrote it on my first slide. Newton concluded that, according to his third law, gravity must be working the same way as well. So if I drop this pen right here, gravity is going to cause the pen to come down towards the Earth. Newton concluded that the Earth is actually coming back up towards the pen. He said that both of these things are happening simultaneously, which seems so weird to think of, because like, how is the Earth moving up? Well, he had a reason for that. He figured, well, it has to do with mass. Okay? This guy has such a small mass that we're going to notice this mass moving down towards the Earth. But the Earth is so excessively large that it moves, but it moves like so infinitesimally small amount that we can't actually tell the difference. Okay? And that's what I found on this last slide here. Okay? The idea is that Earth is pulling a person down with a force equal to their weight. But at the exact same time, the person is actually trying to pull the Earth back up with a force equal to their weight. Well, I mean, imagine that you were trying to pull the Earth not with gravity, but with a rope. Would that work all that well? Well, no. The Earth is so incredibly large that you probably couldn't actually pull the Earth up towards you. What it would look like, though, if you had a rope and you were trying to pull yourself into the Earth, it might look like you were actually pulling yourself into the Earth, but you wouldn't be able to tell that the Earth was also slightly moving. Sean?
Is that why planets work with the sun?
Good. That's where I'm going to go next here. Okay. Gravity is more than just between like this pen right here and the Earth. The reason why our planets orbit the sun is the sun is so incredibly massive that it actually has its own gravitational force, and it causes our planets then to like stay that same distance away. But according to Newton's first law, inertia, because they were already going in a circular motion, they stay going in circular motions. But they always stay like the same distance away because gravity is keeping like Earth from like flying off into the middle of the solar system. Does that make sense? Okay. I'm going to do something I hate doing. I'm actually going to read word for word off my slide here. Okay. So Newton hypothesized that any object which has mass is gravitationally attracted to every other object which has mass. And the force between them is the gravitational force, and it is totally dependent on the mass of the object. Side note here. Sean, you're a little ahead of me. Earth and the moon. Why does the moon not just fly off wherever the heck it wants to go?
Because the Earth has a gravitational pull on it, but it's
Exactly.
hanging off that.
Now, let's say you as a person were out there in outer space. Does the Earth have a gravitational pull on you? Well, yes, but it is so weak because you are so small. But the moon is so large that now Earth and moon can actually have like some gravitational attraction between them that's noticeable. But if you, as a little speck out there in outer space, like in terms of scale, this is a scale diagram of Earth and moon, you as a person would be not even remotely close to that dot right there. Right? Like I don't think I could even draw a pixel that small. Does that make sense? And so based on size, gravity for you out there is pretty irrelevant because you are so small, but there is gravity from the Earth on the moon. And vice versa, by the way, the moon exerts gravity back on the Earth. Now, there's actually a really common example of this. It's tides. Do you guys know what tides are?
Yeah.
Okay, a good example is in the Bay of Fundy off of Nova Scotia, Newfoundland. Like the water will get pulled in and out over the course of the day. The reason why tides exist is because of the moon. The moon is so massive, and so is Earth's water, because so much of Earth is made up of water, that depending on where the moon is, if the moon is on this side of the planet right here, it's going to be trying to pull all of this water slightly towards it. Now, I mean, it's not a lot, but it's enough that if the moon is over here, you might have high tide. Or if the moon was, say, somewhere else, you might have low tide. Does that make sense? Okay. Let me keep reading here. The larger then the masses of the objects, the larger the gravitational forces. So for example, on the moon, there is less gravitational force between an astronaut and the surface of the moon than there would be on Earth. You guys ever seen like people, like videos of like Neil Armstrong on the moon when like they bounce? They can get a lot of height to them because the moon is not as big as Earth. And so because the moon is not as big as Earth, the amount of force between the actual moon itself and and the person on the moon is not that much. And so you can bounce higher. Does that make sense? Whereas on Earth, gravity is a little bit stronger because Earth is bigger, and so it keeps you tied down more. In theory, if you were to go to a larger planet, like say Jupiter, or the sun, imagine you could actually live on the sun. It's not like 3 billion Kelvin, right? You probably wouldn't be able to survive there because the gravitational force between the large sun and you would be so strong, it would actually compress your body, and you would like get squished right into the, it would try to pull you right into the middle of the planet. Astronauts often undergo some interesting, Who grab breakfast? I'll finish my thought in a second.
So if it was possible to be at the center of gravity, gravity trying to pull you there.
Yes. So that would be interesting because you're inside, and so therefore I would think that it might be less because the gravity might be trying to pull you back. Like if you're right in the middle of it, there is mass around you that might be trying to pull you back other directions, so it might be a little bit less. I might be able to agree with that. I don't know the answer to that though.
People
We'll look into that.
that go to space for long periods of time, they grow
That's actually what I want to talk about next, yes. Yeah. Haley just pointed something out that I was going to mention next. People who go into outer space for long periods of time, they often grow. And the reason why is that when you walk around on Earth, you are getting compressed by gravity. Gravity is trying to keep your body being forced down. Well, with less gravitational attraction, your body has nothing like keeping it squished down, if that makes sense.
So you come back taller.
And so you come back a little bit taller. Yeah.
Let me get you again.
If you were to, say, go to a different planet that was heavier than Earth, you might actually find it very difficult to walk. Because, I like to think of magnets then. Imagine that the magnetic strength between you and the planet is so strong that you can't physically lift your foot off the ground because the attraction between the Earth and you is so strong that you'd be stuck there. Does that make sense?
So it almost makes you feel a lot heavier just because of the different gravity.
Yes, and that's the term we want to use here. I'm going to get to this later here. You're going to feel heavier based on what planet you're on, or you might feel less heavy. You guys ever heard the term weightlessness? You use that term when you go into space. You still have mass. You still exist as a person. You're still a real person. You still have mass, but the amount of force, the amount of we use the term weight that you have would actually be less, and that's why people float in space.
95 just
Question?
to die, and then I got it
I found this diagram online. I hope this kind of helps illustrate my point. The apple right here that this person is holding, it is being gravitationally attracted to the Earth. So this apple is being pulled down into the Earth. And technically this Earth right here is getting pulled back up. But we don't actually notice the Earth getting pulled up because it's so small. But this apple is also gravitationally attracted to this person right here. Because this person has mass and this apple has mass. Is there a lot of gravitational attraction though? No, it's so small. Here it was 0.89 newtons, and in this diagram here they calculated it as 4 times 10 to the negative, 11 maybe newtons. But there is just the slightest bit of gravitational attraction between every item that has mass. Give me 1 sec here. No, it's not one of them. Okay, here's a weird thought then. Every item that has mass is the source of its own gravity. You have mass. Therefore, because you have mass, that is the reason why gravity exists for you. Gravity exists for you between you and the Earth, but it also exists for you between you and that stool, and it exists for you and those racks up on the top there. But is there a lot of gravitational force between those? Well, no, because that and me, there's not a lot of mass there. Me and the Earth, though, now there's enough mass to make it worthwhile. Does that make sense? I had a friend in university. He would always have a funny joke he'd say. Maybe you find it funny, maybe you won't. But he'd always say that he was the most attractive person in the room. He was a large guy, 350 pounds, really big guy. He probably wasn't the most attractive person in the room. But then he'd say afterwards, gravitationally. Because the reason is he's the biggest guy in the room. Therefore, he has the most gravitational force. So, it wasn't that great of a pickup line. I don't think so. No. So, other side notes. A couple of you guys were in my Science 10 class. I'm thinking Raj and Nicole, you guys were in my Science 10 class. I once showed a video to some of you about how scientists believe the universe once was formed. Maybe you've heard the theory like the Big Bang Theory, not the TV show, but like the actual theory. There are some scientists who believe that gravity is actually the reason why our universe exists the way it did. Originally, there was a whole bunch of mass, and it had to clump together to form like larger particles. So like think chemistry. You've got all of these elements in the periodic table like hydrogens and heliums and really essentially you have protons and neutrons and electrons. Well, what caused them to clump together? Gravity. Right? Gravity causes this thing and this thing right here to want to come stick together, and that is how mass was hopefully like formed. That's one of their theories. Okay. What should I talk about here? So another reason why objects don't just fly towards each other is distance as well. Okay. The further the distance away, the less the gravitational effects. If that makes sense. So that's why when you're in outer space, because you're so far away from Earth, the force of gravity is lessened. Again, it's kind of like magnets. You have two really strong magnets, you put them really close together, what are they going to want to do? Well, they're going to want to click together like that, right? And what would happen is this magnet and this magnet, they'd kind of meet halfway in the middle. Like they're both attracted to each other. Take those same magnets and remove the distance. Are they actually going to want to try to come together as much? Well, they'll still want to try to come together, but it won't be nearly as strong. Does that concept make sense? So there are two main factors for gravity. The first main factor is mass. The bigger things are, the more gravitational forces there would be. But the second factor is distance. The further apart they are, the less gravitational force there would be. So I found this picture on here of people out in outer space. Gravity would have more effect if the space station was on the surface of the Earth, but take that same space station and move it way out into outer space. Now you're so far away from the Earth that gravity is having a harder time take hold. Does that concept make sense? Sean?
Does that mean if like the needle is small enough, it could just like go off? Like I know it's not a bit fun anymore, but it could really just go off like that.
Yeah, that's kind of the concept, is that like it would be, for its distance from from the sun to Pluto is so far that there's not really a whole lot of gravitational force there. The one thing that does keep it though in motion is inertia. So now that it's been in motion, doing its whole circular motion here, unless some other force alters it, it should stay doing that for forever. Does that make sense?
So if we were hit hard enough by like another planet, would we like go
There
off?
are some theories about that. That it, like, hypothetically, imagine that Earth was hit by a large asteroid, and somehow Earth survived. Because like you've probably seen like science fiction movies, right, where the asteroid hits the Earth and everyone dies because like it changes the conditions of Earth. You know, like biological conditions, like its atmosphere, or that sort of stuff. The theory would be that it might be large enough just to knock Earth slightly off its orbit, and then its orbital path might change slightly. So that could be dangerous. But
Do you have like longer days or shorter days? Or like,
Or
makes sense.
would it make it so that not enough sun would reach?
that could happen too. I think there's too many variables to account for here, right? But that would be the idea, that like it is possible that if another force altered Earth's trajectory, that it would now be on a different rotation, right? Rather than being here, it might now be further out. And being further out, maybe we wouldn't get enough heat from the sun. And I mean, Earth is like perfectly positioned for life. Like the amount of energy we get from the sun is just perfect. Because if you go one planet away from us, the Mars is too cold, and one planet closer to us, Venus, is way too hot. So like Earth is like right in the right spot.
So in theory, could there be an asteroid with enough, I don't know,
Force, we can use that term.
Yeah, so to hit the Earth and completely stop it because of like that their spot, or no?
I would imagine that it would have to be a planet then that would be the exact same size as Earth, moving the exact same speed as Earth. But I guess that would make sense, right? If you had this guy moving with a mass and an acceleration, and this guy moving with the exact same mass and acceleration, and then like they could come together, collide, and stop. I guess that in theory that could happen. I don't know why there'd be another planet the size of Earth hitting us, but
But could we
you get some weird ideas here, though, right?
if we get hit by something though, and it doesn't actually like ruin our course or whatever, but can it make us go faster? No, we'll have like short
I mean, I'm starting to ask some questions I don't know that I have the answers to. Maybe it could cause Earth's spin to happen a little bit faster, maybe.
Because like if you're like pushing something and it won't actually go different, it'll just keep going.
I don't know. Jack, you had a hand up a second ago.
Yeah. Do all the planets rotate? Like, obviously, it's not just on flat plane, but do they all go in the same direction, or is it just like completely random?
I don't believe they all go in the same direction, and they also like imagine it's 3 dimensions, right? One could go like this, another one could go like this, another one could go like this. Another thing that we're going to talk about when we get to circular motion is they don't actually rotate in perfect circles either. They actually rotate in slight elliptical orbits, which is also another thing to account for. I hope that answered your question. Okay, let me get back to my notes here. Here's a diagram then that I need you guys to be able to recognize. For those of you guys who are in my, who've taken 20-1, do you guys recognize this graph shape?
Looks like a curved line. So wait, give us a hint. What's the percentage?
Yeah, this is known, and for you guys in my grade 11 class, we're going to talk about this graph shape later. This is known as a reciprocal graph. It is like the graph 1 divided by x. Is this graph right here. Okay, now here's where things get confusing because we're going to call this thing an inverse relationship. But we're doing inverses in Math 30-1 right now. Inverses sometimes have more than one meaning. Sometimes inverses mean you flip x and y around, which is what we're doing in math. But in physics, if we call it an inverse relationship, this is an inverse relationship. As you get further away from Earth, the amount of force goes down. Does that make sense? So like as the distance from Earth increases, the amount of gravitational force you have is way less. Okay. For you guys in my grade 11 class, I'm going to show you these graphs a little later on in the year. It's actually not that much further away, but it's a very common graph. Okay. Here's what I need you guys to know then for terminology. There is what's called a direct relationship between mass and gravity. Okay. If I were to draw a graph here of the force of gravity and mass, as mass increases, so does gravity. So that would mean that it would be a direct relationship. Another term we use for these guys here is linear. And I think everyone here knows like what linear graphs are, right? Like y equals mx plus b. I hope so. So as mass goes up, so does gravity. So Earth is heavier than the moon, therefore there's more gravity on Earth than on the moon. Okay. But it's an opposite relationship for distance. I'm going to use r. R usually refers to like radius here. Okay. The graph you'd have here is that as your radius or distance increases, gravity goes down. Will gravity ever become zero? No. There will always be some gravitational attraction there, which is an asymptote, which now relates a bit again to what we're covering in math. For those of you guys in my Math 30 class. Okay. We'll talk about that next 2 weeks from now. Okay, one more picture here. Oh, Devin. The littlest amount. Like between me and Pluto, there is a little bit of gravitational force. It is not noticeable, but there is still some. That's the idea, right? But between me and the Earth, there's lots for a couple of reasons. One, Earth is way bigger. Two, the distance between me and Earth right now is not that far actually. I am a foot and a half off of the Earth, so there's a lot of gravitational force pulling me into the Earth. Does that make sense? But if I were in outer space, like say I was on a rocket ship that was just entering outer space, well, I would still have some gravitational force, but it would be a little bit less. The further away you get, the less you have. Okay, do you guys have your formula sheets? Grab your formula sheets. I need to show you a new formula then. I said to start class, in my opinion, this is probably one of the most, like, I don't think you could rank them, but probably one of the top 10 discoveries in physics history, probably. The discovery of this formula here, because it allowed us to now talk about universal gravitation. Gravity is now not just between you and falling, but between objects everywhere. And like I said, I mean, how would we have space exploration if we didn't have this understanding? Here's the formula that was then discovered. The force of gravity is equal to 4 main variables. Okay. First variable you need to know, mass 1. That would be like my mass. I need to know how heavy I am. Okay. That impacts things. You also need to know the second mass. So that would be like, well, how heavy is the Earth? Okay. So you need to know how heavy the two masses are you're talking about. You also need to know the distance between the two objects, which some formulas use the letter D and some use the letter R. Which one does yours use? R? Okay. R sometimes refers to radius. Okay. I'll come back to that later. The last thing you need to know is that there's also a gravitational constant, which is G. Again, I wish all of you had taken 20-1. I'm sorry, grade 11s. Grade 12s, this is like a leading coefficient. You know how often in examples I make you guys put an A value out front? This is that A value that you have to solve for. Okay. Sorry. Sorry. I'd have to teach you like another couple of months here. I found another picture here that maybe hopefully makes sense. Same formula. There is this value out here for G, which is it's called a leading coefficient. You guys maybe know that term, right? Have I talked about leading coefficients before? Okay. Sorry. I don't know how to give you like the Cliff Notes version at this point right now. Long story short, this guy right here is not an actual variable. This G right here is a leading coefficient, and it is always the same number we've discovered. We've discovered this number is 6.67 times 10 to the minus 11. Okay, if you flip over your formula sheet, there's like some constants listed on one side there. And hopefully you'll see it listed quite close to the top. Capital G is equal to 6.67 times 10 to the negative 11 newtons meters squared over kilograms squared. Okay, we've discovered that this constant exists everywhere in the universe, or at least to our best of our knowledge, this is a constant value. Kind of like I said, if you're in my math class, this is like that leading coefficient that an equation might have. Okay, which leads to some obvious questions. Who in the world figured that out? How do you solve for that? Okay, so I need to tell you guys a bit of a story. Years, I believe it's actually over 100 years after Newton did his work, Newton concluded that, he's got these 3 laws. He concluded that as masses increase, gravity increases. He concludes that as distance increases, gravity decreases. But he couldn't quite piece it all together because he was missing what was called a gravitational constant. This guy named Henry Cavendish came up with this experiment. So let me try to describe it to you. He had large masses, like really heavy masses. I imagine he probably used lead. The reason why he used lead is like the most dense material we have. Okay. He attached like a large mass right here, and this figure right here doesn't show it, but they should have been attached by like a rod across them. Okay. And then another rod would have had other masses. Now this picture here shows them being like drastically different, but I imagine they were probably fairly close in size. And what he did is he put them very, very close to each other, so that what should happen here is that there should be a force of attraction between these two masses, pulling them together. That makes sense? Now it would be ever so slight, because are these masses very large? Not really, not compared to the Earth or the Moon or the Sun, but he put them really close together. And what he measured then was torque. Do you guys know what torque is?
Oh, it's when you're
like when you're twisting something. Torque happens in like a circular motion. Probably the best example I can give you is you go to get your tires changed. For like you take your summer tires off, you put your winter tires on, And in order to tighten the lug nuts on your tires, they torque them by having it like twist. Okay. Well, what Cavendish did is he measured how much twisting there was between these two wires after they came together. And he used that then to go backwards and calculate the constant for G. Now, what he ended up doing then was publishing his findings in a paper called Weighing the Earth, because he ultimately figured that he could then figure out how heavy the Earth was based on this information. And we're going to try to do a few questions here. Okay. Let me show you some more pictures though. Nowadays, we don't do it quite with that old technology. We now use mirrors and lasers. Same concept. So let me see how I can describe this here. Same thing here. You're going to have big mass, little mass, little mass. And what you're going to try to do is put them close to each other so that, say the mass was right here and it was right here. What would happen is this mass would get pulled towards that mass and this mass would get pulled towards this mass. Does that concept make sense so far? Would it move a lot? No, ever so slight. So how do you measure that? Last picture. This one's probably the best one. You use a mirror and a laser. Imagine that you were using a laser shot at a mirror right here. But the mirror was on top of the rod right here that was going to move. So let's say this guy was going to move this way, and this guy was going to move this way. If the mirror moved ever so slightly, and I mean we're talking like nanometers, well, as this laser right here shoots from here and moves over here, if this thing rotates here, the mirror itself is on top of it, the mirror would also slightly rotate. Does that make sense? And what would happen then is the laser normally would have shot from here and bounced to there. If the mirror were ever so slightly moved to like there, then perhaps it would cause this thing to move and shoot there. And using some trigonometry, we can then calculate how far this is moved. And he reverse engineered this to basically calculate how much the gravitational force, like the big G letter, was.
How did he figure that out?
To be honest, I'm not sure how he managed to figure that out, but that's like the basics of how he did it.
This
So-
guy get like Nobel Prize or something? Is that-
I think this was before Nobel, because Nobel was a little later, but yeah, he would have earned one. This was, in my opinion, one of the greatest accomplishments in physics history was calculating G, because it now gave us this formula. I'm going to go back here. This formula here that we can now use to calculate gravity anywhere. So rather than using 9.81, we can actually use gravity anywhere we want in the universe, so long as we know 3 variables and a constant. Variable 1, what is mass of one object? Variable 2, what is the mass of the second object? And variable 3, how far apart are they? Questions? You go first. Go ahead.
Okay. So I see that we have that nice little equation right there.
Okay.
And so far we've been given equations, but we've had to like do this first and then do this and then do this and then or you have to do with this.
Yeah, sure.
Joy.
Okay, now this equation is a little bit bigger, but it's not necessarily harder to use. Okay. Before I do that though, I want to do one more thing and then we'll actually do some practice questions. Cavendish published a paper where he felt like he could actually find the mass of the Earth. How in the world can you weigh the mass of the Earth otherwise? It's not like we can grab like a really big scale, lift Earth up, and put Earth on that scale and weigh it. Okay. Here's how he figured he could calculate the mass of the Earth. Okay. The formula that they discovered was that Fg was equal to big G m1 m2 over r squared. But there's another way to calculate gravity. How have we been calculating gravity up until today?
Mass times gravity.
Okay, so he said that it could also be equal to mass times gravity. Make sense so far? So he combined 2 formulas and said mass times gravity little g should be equal to big G m1 m2 over r squared. Now I gotta be a bit more specific. Let's say that the thing that is having gravity attracted to it is you. Okay, so you are a person. So why don't I make this mass 1 be the mass of you? Well, if I wanted you to calculate your gravitational force up until like yesterday, that would have meant that this mass right here would also have been your mass. Which means that he can take this mass right here and this mass right here and cancel them. What would M2 be? Earth, yeah. Because really, what are the two objects we're talking about? Well, you and the Earth. So mass 2 was the mass of the Earth. So then what he did is he said, well, how do I rearrange to get M Earth by itself? So now that these masses have canceled because they're of the same thing, he then took r squared, times it up to the other side. So he did g r squared. He divided by the capital G that he just solved for in his experiment, and he said, based on this information, I believe I can tell you what the mass of the Earth is. So all you need to know is little g, 9.81, which they knew at that point. You also need to know the radius, the distance between you. Now, this was actually the distance between you and the center of the Earth. We went to the center of the object. Well, which is the Earth's radius. And mathematicians had actually calculated Earth's radius long, long ago. It's actually on your data sheets. If you guys want to look it up, we actually think we have calculated the radius of the Earth. Like Pythagoras, like old Greek mathematicians had figured it out. Do you guys have that number nearby for me? Meters?
Excuse the interruption. All grade 6 students who have not had your pictures taken, please go to the drama room now. Grade 6 students, please get your retakes done now.
Okay, so based on this, Cavendish said, gravity I know, we've calculated a long time ago, it's 9.81. The radius of the Earth, he also knew. Ancient Greek mathematicians had figured it out a long time ago. I can show you that proof if you care, but that's another lesson entirely. Okay. And he just calculated G doing his experiment, which is 6.67 times 10 to the negative 11 kilogram. What are the units again? I always forget this one. Newton squared over meter squared? No, it's Newton meters squared over kilograms squared. I'm gonna remind myself this. Haven't used it for a while. It is newtons meters squared over kilograms squared. Okay. When you guys type this in your calculator, I need to do a couple of things. Make sure that when you divide by this number here, put it in brackets.
You just square your radius, right?
You do need to square your radius, thank you. I missed that, thank you.
That's what I got. You square your radius.
You did square your radius? Oh, yeah, just square. Oh, I see what I did.
So take 9.81 times by 6.37 times 10 to the 6, put that in a bracket and square it, and then divide by 6.67 times 10 to the minus 11. And hopefully you'll get about 5.98 times 10 to the, I think is it 24 kilograms,
I didn't get that.
which is how heavy Cavendish believed the Earth was.
Haley, did you get that point something? Okay, you did what I did first, you didn't square the entire, radius, you put the square by the,
9.81.
yeah.
This squared I wrote right here though is in the units, not actually in like the actual number here. Like meters per second squared is the units. The square we need is right here.
I put it inside.
This is 9.81, but it's like we don't square that number. Then we times by the 6.37 times 10 to the power of 6. We square that. And then we divide by 6.67 times 10 to the power of negative 11.
Oh, okay.
Just want to change this. Was this a 9.7? 9.7, sorry. Okay. 9.67, so it rounds up to, rounds up to 7 then. Is that your question? Yeah. Okay. Can you guys take a look on the back side of your formula sheet? Because we actually have a value that we believe is correct for this. And I believe the accepted value is 5.98. Did they go with 9.8 on that one? Well, they did go 9.7. Okay. Okay. Which indirectly is how much we believe the Earth weighs then. Not that we could ever like take the Earth and put it on a scale, obviously, right? But indirectly, this is how much we think Earth weighs. From now on, then, when you want to do a calculation, you're going to need that number if Earth is the thing that's providing the gravity. So I've got half an hour left. Let me show you some examples of some questions I might need you to solve. So here's the first one. Mount Logan is 59 meters above sea level. If you were 55 kilograms, how much would your weight be at the top of this mountain? Now, a couple of things here. Weight is a little bit different than mass. Your mass is 55 kilograms. Your weight is like how much force you have getting pulled down towards Earth. Because I used the term weightlessness before. If you were in outer space, you would be weightless. Meaning that, but you'd still have mass. You are still a person. You still have molecules in your body, right? But you would feel weightless. You would just float around. Okay. On top of a large mountain, gravity actually has less effect, if that makes sense. And if you went even further up into outer space, you'd feel even less effect. I've got a slide afterwards here that I just want to use to illustrate things. Your weight is actually based on gravity. Weight is in newtons. So I just found this slide here. Hopefully this makes sense. Mass is in grams. We don't actually care about density, but it was on the slide. And weight is in newtons. So weight is how much your mass is times however much gravity is. People often use those terms incorrectly. If I ask you to go weigh yourself, and you come back with the number for mass, that's actually, according to physics, that's not what I'm looking for. Weight is actually based on like how much force something has. You could do by just doing that. That's why I threw that formula here. Weight is just mass times gravity. Mass is just mass. Okay, so let's try this here. If I'm looking for weight, I'm really looking for Fg. Okay. So from now on, if I ask you for your weight is the force of gravity on you. The formula for that is big G times by mass 1, mass 2, all over your radius squared.
What is the big G?
Okay, so this is that like leading coefficient constant that needed to be calculated to make the formula work. Like, you know how we often have to do this in our math class to like make the formula work? There was a leading coefficient constant they just couldn't find until they had all these variables, and that's what Cavendish had to solve for. Once he'd solved for it, now we can use this formula whenever we want.
Does it, like, what part of gravity does it represent? I don't know. I just don't understand what it is, the canceling coefficient of the
That's
calculation.
pretty much, that is the definition. Like, it does not have any meaning. Like, the units, meaningless. The actual value of it, meaningless. All it was is it was the number that, like, pieced everything together perfectly. We've actually discovered there's quite a few of these sorts of things that are found in physics here and there, where like there's a coefficient that's necessary. Probably the closest comparison I can give you is it's like the coefficient of friction. The number for the coefficient of friction, kind of irrelevant. If I tell you that it's 0.21, it doesn't mean anything. It doesn't really have purposeful units, but it's just a number that was needed to help us solve for it, which is like a leading coefficient. Okay, let's throw some numbers in. Big G then is that leading coefficient of 6.67 times 10 to the minus 11. I'm gonna get my units right this time. It's newtons, meters squared over kilograms squared. Meters. We need to know M1 and M2. What are the two masses in question here? Well, one of them is U, which is 55 kilograms. What's the other mass? Earth. Earth is the other mass. So then Earth is going to be, what did we just calculate it at? 5.97 times 10 to the 24 kilograms. Running out of room there. Okay, a couple of notes here. See how you have kilograms squared on the bottom here? Well, one of those kilograms will cancel with this kilogram here. And the other one of those kilograms will cancel with this kilogram here. So in terms of units, this one and this one would cancel with both of those guys. The second thing we've got to figure out is what is our distance away from like the center of the Earth? Well, that would be from sea level, but then we have to add on the fact that Earth itself has a radius. So a little side note here, your radius that we're going to calculate here will be 6.37 times 10 to the 6 meters plus an extra 59 meters. Does that make sense? You have to take the radius of the Earth, but add on the fact that you're on top of a really high mountain. So you could actually do that all in one step here. You could take your 6.37 times 10 to the 6 meters plus your 5959 meters. And just don't forget to square all of that when you're done. So I'm going to grab my calculator and make sure that I'm typing this in correctly. So 6.67 times 10 to the power of negative 11. I'm going to times them by 55, because that's my mass. I'm also going to times by 5.97 times 10 to the power of 24. So that's the mass of the Earth. And then I've got to divide by, and I'm going to use a big bracket here. It is 637, right? That's the value that's on your data sheet?
Yeah.
Sometimes I've seen it as 638. It depends on who's rounding. Times 10 to the power of 6 plus your 5959 and then square that. I got 537.
I got 538.7.
Yeah, me too.
I got like 1.53 times 10 to the power.
So is that how much, how many
Oh, let's
meters?
get this.
So that's how many newtons worth of force you would have.
You use 6.38. You use. I didn't get that.
Oh, I screwed up. I used 3.8, didn't I? Thank you. Let me go back up here and try that again. Even after I said 6.37, I still used 8, didn't I? Okay, let me do that one more time. 6.67 times 10 to the power of negative 11. Oh my goodness. This thing just locked up on me.
Other.
10 to the 11 times 55 times 5.97 times 10 to the power of 24 divided by 6.37 times 10 to the 6 plus 5959 squared. Okay, 538.7.
That's what I got. Exactly.
Okay, I'm going to write down that whole value here. FG would be equal to 538.7308. What if you were to have calculated gravity then, just based on like the old-fashioned way that we do it, where it's mass times gravity? It should be nearly the same. Watch this: 9.81 times 55. But it's 539.55. Why is it less?
What 8.1 is about it?
You're further away from the Earth. The further you are away from the Earth, the less gravity will actually impact you. And so because you're way up on top of the mountain, your weight, which is how much force of attraction there is between you and the Earth, because you're farther away, gravity should actually be slightly less. And so this calculation we did here, which is rather complex and rather large, is probably more accurate than just timesing by 9.81. Yes.
Could we do the same thing if we were, say, standing on a mountain like Mars?
Sure. Yeah, and that's actually where these questions are going to go. The next two questions I've got are going to be like interplanetary type questions. Because when we're on Earth, it makes more sense on Earth just to do 9.81 and call it a day. But when you're doing like large universal calculations, like on Mars, on the moon, on stuff like that, that's where this formula comes in. Okay. Does that make sense?
What did you mean by like less? Like the one that we just calculated is less than the
Yeah.
force of gravity? That's what you
Yeah, because like the old-fashioned way we calculated it, you would have got 539. but the new calculation was 538. Like, it's hardly different. But the reason why it's slightly less is that as your distance from Earth becomes further away, there should be less gravitational attraction. It was not much less, but it was a little bit less.
So if you would have just calculated without the 5,959, it would have been the exact same.
It should have been, hopefully, basically the exact same. Yeah. Yeah. Sorry, today was a long lesson. I apologize. Okay. Let me do one last example here, and then I'll call it a day. Oh. Okay, you can't wait. Sorry. This is my last one. Here's a typical example of what I might give you on like a test or a quiz or something. On your assignment, I believe one of your last questions, if you've looked that far, is about finding gravity on the moon. Okay. So if you were to be asked to calculate things on other planets, this is where this formula comes in. Io is one of Jupiter's moons. Imagine that this scenario happens. Io is close to Jupiter, so there's gravitational attraction between Io and Jupiter. But Io is also gravitationally attracted by the sun. By the way, Io is also gravitationally attracted to me. But is that a lot of gravity? Not really. But the sun is pretty big, so it's worth calculating how much force of attraction there would be between the sun and Io and Jupiter. But is it really relevant to calculate Io's gravitational attraction to every other thing in the universe? No. So we're only going to actually calculate like large objects, if that makes sense. So our goal, let's find the net force acting on Io. It's a moon of Jupiter. Sean.
Would you have to minus the pole of the sun from the pole of Jupiter?
Yeah.
Because the pole of Jupiter is greater?
Hopefully it is. If not, then Io is ultimately going to be slightly moving towards the sun. I'm hoping not, but we'll see. So let's try this. First, let's do Io to Jupiter. So your force of gravity will be equal to big G. So 6.67 times 10 to the negative 11. Newton meters squared over kilograms squared. I'm going to get those units down by the end of the day. Now we need to know the mass of Jupiter and the mass of Io, which I'm giving you in the chart here. So Io is that many kilograms, and Jupiter is that many kilograms. And then we've got to divide by the distance
Wait,
between
are you
them squared.
multiplying 8 point by this 1.9?
Yeah, sorry, I just ran out of room there. So all three of these numbers times by each other, and then we have to divide by the distance squared.
Are you using 1.99 or 1.90?
Thank you. 1.9.
Oh wait,
No, it should be 1.90.
I looked at
This one's the mass of the sun. So distance from each other. So how far apart are they? So that would be from Io to Jupiter is 4.22 times 10 to the 8 meters. And just make sure that you square that. Just so you guys know, I'm not needing you guys to use this like sort of formula all the time. It's a rare sort of thing, right? We only use it when we're calculating things that are not on Earth. Hence the term universal gravitation. So please don't feel like this is like all we're going to be doing from now on. 6.67 times 10 to the power of negative 11 times 8.93 times 10 to the power of 22 times 1.90 times 10 to the power of 27 divided by bracket 4.22 times 10 to the power of 8 squared. I got 635, 10 to the 22. So as a moon of Jupiter, The reason why this moon is not flying off into the distance is because there's a force of attraction between this moon and Jupiter, keeping it close enough nearby. Now, because it's in motion, it's going to keep circling around it. That's Newton's first law. But that's the first force. Okay. Second force, then. We now need to find out the force between Io and the Sun. So, hardly anything changes except for two numbers. 6.67 is still there. Newton meters squared over kilograms squared. I'm running out of room here. We're going to have to multiply by Io's weight, which is still this guy. And we still have to multiply by, this time it's the Sun though. The Sun was the 1.99 10 to the 30. Is that right? And then the distance between them is 798 E11. Okay, 6.67 times 10 to the power of negative 11 times 8.93 times 10 to the power of 22 times 1.99 times 10 power of 30 divided by, not the power of, divided by 7.98 times 10 to the power of 11 squared. Okay, here I got 1.86 times 10 to the 19 newtons. Okay, I want to make a point with this though. Try subtracting from your calculator. So like take 6.35 times 10 to the power of 22. Subtract 1.86 times 10 to the power of 19. Boy, that changed a lot, eh?
So the sun basically doesn't affect
Is there gravitational force between it? Sure. There's actually a lot. I mean, if it were you and me attracted to each other that much, or like me and the sun, I mean, we'd get pulled directly in there, right? But because it's so close to Jupiter, it hardly affects it, but it affects it a little bit. And here's how it affects it. I mentioned this earlier. They don't go around in perfect circles. They go around in ellipses. It slightly warps the circle depending on how close the moon is to the sun. Does that make sense? So because there's other bodies out there, rather than like, you guys know how like if you're in grade 5 and you make a solar system and you put the sun in the middle and like everything is a perfect circle? If you were to actually look into this more, it's not perfect circles. Often it's a little bit more of like an elliptical shape. That might have been too much. That's one of the reasons why. Is that other planetary bodies are going to cause this to be slightly different. So it's not a perfect circle. So does that point make sense here? The amount of force that the sun had on Io, it's a lot, but it's ultimately irrelevant. It hardly made a difference.
Please excuse the interruption. Grade 7 students, please go down to the drama room for your pictures. Anybody who has not had their picture taken, these are retakes for grade 7 kids.
Deb.
So is there really no other planets other than the sun that we have a perfect
I think so, yeah. I think then it would probably be a perfect circle. You guys ask a lot of really good questions because like these are hard questions, right? Like this is all hypothetical. I can't go out there and check. It's all like based on what we think. One more thought here before I ask you a question. I said this a few times today. This was groundbreaking for space travel. Okay. In order to calculate how to travel from planet to planet, we needed to know things like, well, how heavy are these planets? Can Voyager, you guys know what Voyager is? like a space probe that tries to take pictures across the universe, could it land on the surface of Saturn? Or is Saturn so large that it would crush Voyager and destroy it? Right? Like, those are good questions to ask. Before you go sending Neil Armstrong to the moon, we better know whether he can actually survive there. And so that's why I think this is one of the most important discoveries in physics history. Because we needed to know things like, how heavy are these planets? How far apart are they? What would gravity be like on these planets? So that we can actually do something with them. Jack.
Ellipses are what makes the season, right?
Um,
If it was a perfect circle, there would be no seasons.
The tilt of Earth's axis is what makes the seasons. But I'm sure ellipsis probably plays into it a little bit. It must. But Earth's axis is the main reason for seasons. Because based on that tilt, if you were at like the equator, the tilt doesn't really matter that much. And that's why there really isn't seasons in like, say, like Brazil, it's always hot.
Mr.
Right?
Patton,
You get
can
more
you please
extremes
call
the
100?
further north
Mr.
or south you
Patton,
get.
please call 100.
Okay. Okay, quick summary and then I'll let you guys pack up here. This is a typical question I would ask you. So in case you're wondering, well, when do I use this formula? We're only really using this formula when we're not on Earth. Okay? If we're on Earth, use 9.81 for gravity, you're good to go. But like, if you're on top of a really large mountain, it might make a little bit of difference. If you're on the moon, it makes a difference. If you're on Saturn, it makes a difference. Does that concept make sense? So I don't need you to do this formula all the time. It's only going to come up in a few circumstances. It's like most formulas, though. It's fairly straightforward, with one exception. Every single number you use is like crazy, insane big. So you just got to be careful with that. That make sense?
Yep.
Cool. Okay. Tomorrow's a work day. Kind of work on some more stuff. Monday, we're going to do our last lesson of the unit. And then we're finished, actually. Okay.